Okay, so chapter 1, basic principles of fluid power. So some of this is not in the textbook. And first of all, we'll look at a couple of videos, and hopefully this thing won't make all this noise. I think these links are, I'm not sure if the links are on. I know y'all can't hear that because it's coming through my headphones. Let's see if it plays on these speakers now. Still not playing, is it? It's not playing on my headphones. And there's another video that we want to show you.
Water squirts out uniformly in all directions from the holes of the flask. The second fact is that it is hard to compress a liquid. If you try to squash a volume of liquid, you still have that same volume, however hard you try to compress it. A hydraulic system is one that uses the pressure of the liquid to perform mechanical work. Let's look at this device. Two syringes, A and B, of equal size, are connected by rubber tubing. If pressure is exerted at syringe A, the same pressure will be transmitted over to syringe B. We also observe that the syringe A moves to syringe B as shown by the upward movement of the piston in syringe B.
Sorry.
Which we have just discussed. That is, simply, when the liquid is enclosed in space and the pressure is applied, this pressure is transmitted equally. Secondly, liquid cannot be compressed. The hydraulic system makes use of these two facts. It can be shown mathematically that if we make one of the two pistons much larger than the other, then the larger piston can raise a larger load. The hydraulic system can therefore be considered as a force multiplier. Do also notice that the small piston has to move a larger distance than the large piston. In most cases, oil is used as the hydraulic liquid, as it can lubricate the moving parts of the machine as well. The hydraulic principle is used in many devices, like the hydraulic jet used for tilting cars at the service station. Notice that the serviceman has to exert a force on the piston many times before the car is raised by a small amount. Thanks to the hydraulic jack, lifting the car for servicing is no longer a problem. One of the most important components of a car is the brake system. But do you know that the brake system of a car also works on hydraulics? Let's take a closer look at the brake system of a car. When the driver presses on the brake pedals, the oil in the brake system transmits this pressure and moves these pistons. This will cause the brake pads to press against the rotating disc on the wheel. Hydraulics is also used in many heavy machinery in the construction industry, like this loader. Can you see the moving pistons in action? Machines using the hydraulic system are capable of moving very heavy loads. This is a dumper. It also works on hydraulics. The excavator is another hydraulic machine commonly found at construction sites. The hydraulic system will cause pistons to move a part of the machine back and forth. Imagine what it would be like if all this work had to be done without the help of these hydraulic machines. An accident? Thank goodness it's only a practice for the civil defense officers. They're trying to rescue.
Yep. I guess that's it. So what did y'all think? So what's some of the advantages that they talk about on a fluid power system? Force multiplier, right? And of course, they act like levers. Y'all are familiar with levers. you set a fulcrum point, and depending on where you set that point depends. So the closer we get it to the load, the more multiplication we have, but the further we have to move the handle on the left-hand side, right? So we can use them for force multiplication. What's another advantage they brought up is their size to power ratio. So how much power or how much force we can get out of those things compared to the size of what we call actuators, which is really neat. Another advantage is they said you could change directions. Big motors, we can't do that. It's called plugging the motor. If you try to change the motor direction instantly, that's not good. Yeah, anytime if you've got a ceiling fan, everybody's done that where you change the directions on that motor, and as soon as you do it, you hear that sucker just humming real loud, pulling a lot of current, and you can't do it instantly. Well, with fluid power systems, we can change the direction of a motor in a heartbeat, which is really neat. And we can control the speed by controlling the flow. So some safety, hydraulic pneumatic systems use stored fluid under pressure. And of course, anytime we have pressure is trying to push things out, right? So we got to be cognitive of that. Before you connect any lines, you want to try to bleed off the pressure, especially in a hydraulic system. Hydraulic systems run extremely high pressures, and you break those lines loose, and then that pressure is looking to push that fluid out different directions. And we've had people where it comes out with so much pressure, it literally gets that hydraulic fluid, shoots it into their skin, and then it gets really infected because it's not good stuff. Pneumatic pressure is not near as bad. We don't run extremely high pneumatic pressures. Huh? It could, depending on how you get it. The highest pneumatic pressure I've ever seen, and this was when we was up in Tennessee. We were in the Bridgestone tire plant up there, and they used 600 psi. I never seen that. Before that, the highest I saw was at U.S. Steel. The highest they had out there when I was there was 200 psi. Pneumatic systems run the airplanes that hydraulic systems, the airplanes I worked on in the Navy to move the control surfaces ran 3,000 psi. And 3,000 psi will definitely cut you. In fact, I told my other class in the Navy when I went in the Navy last time, that's the way they gave us shots. They used hydraulics shots. So they didn't use needles. They used guns. And they put it on your skin and just pull a trigger and it'd shoot it right into your skin. And like I said, they had a row, had 2 bars on each side, had guys on both sides shooting you on both sides of the arms when you're getting all those shots. Huh? Yeah. I got my shot card. Fluid systems required maintenance. So this is a big problem we have. People don't understand the fluid power systems, and they don't do regular preventive maintenance on them, which causes problems. Anytime you have things that move against each other, you're going to have friction and you're going to have wear, right? Yeah, well, yeah, some of them do, you know. What we do in pneumatic systems sometimes, we either buy self-lubricating valves, which are available, or we put an oiler in the system, which basically squirts a little bit of fluid, oil into the air to keep everything lubricated. Unfortunately, over there on 2 of our robots, we don't have that. And they're not self-lubricating valves. So every once in a while it won't work, and we literally have to take the valves across and apart and oil them. So we do have the lubricators. We just hadn't had the chance to install them in the airline. Most hydraulics, we don't have a lot of problems because most of the hydraulic fluid we use are oils. And what's nice about oils is they're what? They're self-lubricating. So. Check for leaks and worn hoses, keep contaminants out. And by the way, hydraulics also uses oils. And so what happens if you have an oil leak? Now you got slippery stuff all over the place. So a lot of times you have people that go over there trying to work on there, slip and fall too. So in fact, I told the last on Monday, originally we taught hydraulics, and we all the labs were hydraulic labs, and we taught pneumatics because our trainers were hydraulic trainers, and they're trainers. So you would repipe the thing, and every time you took a quick disconnect pipe off, it squirted a little oil out, and it got to the point where we couldn't hardly do anything because the floors in there would get so slippery. We put big old mats down that had holes in them so it could get through to the floor, but after a while the mats would actually start slipping. So the mats actually interlocked and they covered the whole floor in there. And like I said, we'd have to have the cleaning crew go over and clean up all that oil all the time. So now what we do is we teach hydraulics and pneumatics, but all our labs are on pneumatics. So if you have a leak on a pneumatic system, it's not going. On ours, we run, I think 60 psi, which is not very dangerous. So this is fluid power. This is the definition of fluid power. So we're going to use a confined fluid under pressure to transmit power from one location to the next. That's what fluid power is, and that's what I would like this course. I'll call this fluid power, by the way. Even though the course is hydraulics pneumatics. So fluid is a substance that has no fixed shapes and yields easily to external pressure. Unfortunately, most people think of fluids as liquids, but that's not true. So fluids can either be a liquid or a gas. Everybody understand that? So half my life when I got here, when we started talking about fluid power, I thought about hydraulics. So I didn't even know that when I started teaching here. We have two main uses. We can change directions of the flow easily, and of course, force multiplication is the big thing. So that means we can put a small force in and get a large force out. And of course, the two areas are what? Hydraulics and pneumatics. That's those are the two fluids. Are we okay? Yeah, these slides are up there. So hydraulics, this is when we use fluids to transmit power, and pneumatics is when we use a gas to transmit power. Now, by far, the most popular gas is air, which actually is a combination of combination of gases. What do you say, Justin? Yeah, it's cheap because it's there. And like I said, in some applications, in extremely cold environments, we don't use air, we use nitrogen. And as soon as you use another gas, it's got to be a sealed system, so they become more expensive. No, I've never seen one that's, these are light gases, but when they use them, actuators. An actuator is a device that converts the pressure into motion. So we'll have two types of primary actuators. We have linear actuators and rotary actuators. So y'all know those terms. So linear actuators means it generates a force in a straight line. And then we have rotary actuators, which generate forces in an arc. Then we have another rotary actuator that has a unique name. It's called a motor. So usually when we use the term actuator, it's something that has a limited motion. So it's usually less than 360 degrees. When we use the term a fluid power motor, that's a motor that can rotate unlimited amounts of turns. So even though a motor is a rotary actuator, we split those two terms up. So they compact and have high energy. We already talked about that. Another big advantage of these fluid power systems is we can install these actuators. We can't stall electric motors because if you stall them, they're going to burn up. Okay, but these guys don't care. So you can leave that pressure against one side of that actuator for doomsday, and it'll stay over there and won't hurt anything. So any situation where you're going to have to stall the actuator, it's probably going to be fluid power. Or instantly reversible. Could. I mean, actuator, anything could have a clutch on it, especially a motor. Normally, we don't worry about clutches. So what we do on electric motors, if the system is going to stall, we put a clutch on it, so that way the motor can keep spinning without stalling the motor. You don't see many clutches in industrial hydraulic systems. You do in motorcycles. You know, you have a clutch on your hydraulic system. Huh? Yeah, but you're going from a combustion engine over to something else, right? So that we're talking about a fluid power actuator. So fluid power actuators don't really need clutches because we can stall them; they don't hurt them. Other things like a combustion engine hates to be stalled, right? You understand? Even though I just stalled my motorcycle one time. That was embarrassing. You never did that though, did you, John? Instantly reversible, then we have an infinite speed variation on these things. So we can control the speed real easy. We can reverse them instantly. We can stall them, and we can the power to ratio is a lot smaller. The planes I worked on in the Navy were P-3 Orions, and these were big planes. These guys don't land on ships. They were sub chasers. Their primary mission was to seek and destroy submarines. So this had we were nuclear capable, by the way. So our planes could carry nukes. But it was a big plane. But if you ever looked at the hydraulic cylinders that moved the big old control surfaces, they were less than probably 2 inches of area. But they ran 3,000 psi. So with 3,000 pounds per square inch, and it was actually less than it, but it's 3,000 psi. If you were pushing that against 1 inch of area, you could generate 3,000 pounds of force. So that's what's really nice. You can have these real small actuators generating a lot of force. Could do that with a motor. These are some standards. These are not in your book. Nancy put this PowerPoint together. Now we got two NFPAs or NAFTAs. We have the National Fire Protection Association, which basically deals with electricity, and then we have the National Fluid Power Association. So don't get confused with these two. Protection Association. Yeah. So they do if you ever heard of the National Electrical Code, NEC, that's put out by the National Fire Protection Association. So they mostly deal with electrical things and things that prevent fires from occurring. ATSM, the American Society for Testing Materials, SAE, y'all probably heard about this. Where do we run into SAE? Huh? Well, SAE, but also tools. So we got metric, and then we got the SAE standard, which of course is the U.S. customary standard or imperial standard, where we go in inches, right? You understand? But if you buy the kit, they don't say U.S. customary; they say SAE because those are approved, and you have the metric system. ANSI, this is important. This guy is all over the place. This is the American National Standard Institute. Which is probably, ANSI is a member of ISO, which is the International Standard Organization. And ISO is basically a combination of all these different continents and everybody that has a standardization, and they try to get together and set industry standards. And in ISO, this is very important because these are all international standards. Unfortunately, the United States does not follow a lot of the international standards. We are a stubborn country. Yeah, probably about 20 years ago, the United States tried to convert us over to the metric system. I don't know if you ever remember that. So all the cars that came out had miles per hour and it had kilometers per hour on them, the speedometers. And then on these mile markers, they had two of them out there. They had one for miles and they had one for kilometers. And their ultimate goal was to, over time, to do what? Eliminate the miles, right? Who won out? Yeah. So we're still using feet, and we're still using yards and miles. So ISO is an international standard. They set all the international standards which American does not use. So basically, we have three big standards out there. We have what we call the imperial standard, which used to be the English standard. And then we have what they call the U.S. customary standard. So we'll talk a little bit about U.S. customary, but we'll also look at these other things. In industry, you still, a lot of your gauges now have both the international standard and the U.S. customary standard on there. So because we have a lot of people from different countries, especially in this area now. NAFTA sets up a cylinder sizes, mounting style. So if you've got a NFPA approved or registered cylinder in your shop, that means when you go out and buy one, you could buy anybody who manufactures that makes that same type. So it means you could bring it in and it would mount the same and all that other kind of stuff. So this is the NAFTA. ASTM, these guys are these are voluntary standard development organization. And of course, y'all could read this as good as us can, but this is another one of our testing. This is kind of like UL, where they do what? They're basically a testing organization. It's like Universal Laboratories. Y'all heard of that? UL approved. What did UL do for us? What they do is they verify that a device does what the manufacturer says it's supposed to do. So if you got UL approval and you see, it also deals with safety too. So it deals with all this stuff. So if it's UL approved, then it means that what the manufacturer says it's going to do is been what? It's been tested and proven to be. SAE, of course, we're familiar with that already. They set a lot of standards. They set the size of socket wrench standards. So we have the SAE standard, and then we have the what we call the metric standard. ANSI, this guy here sets all types of American standards, and they may be they're also part of the International Standard Organization. So some of your ANSI standards are going to be using. So we have it administrates and coordinates the U.S. voluntary standardization and conformity assessment system. And then, of course, ISO, these are the International Standard Organization that's made up of member companies. It's kind of like the United Nations, where they get in and they try to establish international standards. And, of course, what everybody tries to do is tries to get ISO to adopt their standards, which is really strange. It took about 15 years for them to come out with high-definition TV. And why? Because we had about Zenith and all these different companies were trying to do their own high-definition standards. And so the problem is that if you're going to come out with a high-definition standard, it's got to be an open technology for one thing, because not only does the TV manufacturers have to do it, but the channels that broadcast that information has to send it in the right standard. And everybody fought over those standards, trying to get them adopted. Why? Because you're talking thousands and billions of dollars, right? Yeah, so it was awful trying to get high definition. Finally, they finally got it out. So thank goodness, so we wouldn't have high definition TV. We'd still be dealing with 320 lines by 60 cycles. This says all industrial plants use some form of fluid power. So air conditioning systems are fluid power systems. So if you got air conditioning in your house, you got a fluid power system, right? If you got a dishwasher in your house, that's besides your significant other. If you got an electric dishwasher, that's a fluid power system. That's the way it washes stuff, fluid power system. You go out there and turn on your hose, you have a what system? Fluid power, yeah. So we use these things for a lot of things. If you got a pressure washer, you got a fluid power system. So compressed air is the most common gas used. Okay. I had a Ford Expedition that had it. It basically had a level sensor on it. So what? So if the rear end tried to drop down, then it would raise it up to the same height. It was real neat. You could sit on the back bumper. And, yeah, it's the airbag system. Yeah. So yeah, we had one on our Ford Expedition. It finally sprung a leak, and it was very expensive to get. Huh? Calibrated springer, just a level sensor on your truck, which indicates if the rear tries to drop down. But it could be a calibrated spring too, if y'all understand what that is. So pneumatics, we use those to operate pneumatic tools, linear motion. We already talked about that, rotary motion. Most of your pneumatic tools, that it's either going to be a rotary or a linear actuator. Fluid, we've already talked about this. Fluid has a what? What is a fluid? Yeah, takes shape of whatever you put it in. Notice if you got a real fancy Yeti cup, you pour water in there, it's going to take shape. The air that's in there takes the shape of whatever it's in, right? Flows easily or moves easily, and of course we can pressurize this stuff. Of course, fluid power we've already looked at, and of course hydraulics. What's hydraulics? We're going to use a liquid to transmit a force, and then pneumatics we're going to use a what? Use a gas. Are we okay? Okay, guys, let's go. You had a backup, so just about everything on an airplane has a backup. Thank goodness. Are we okay here, guys? Any more questions? Force. So that's the definition. By the way, if you look in your course content, I think there's a handout or reference material. There's a glossary in there. There's a lot of terms or terminology that you need to learn. Every trade has its own language that the people in the trade speak. And if you can't speak the language of the trade, then right off the bat, people think you don't what? You don't know the trade. And first, another thing, you won't be able to speak to anybody else in the trade. And of course, if you don't use the language, these guys that understand the language, what are they going to think about you? Yeah, you don't know. This guy don't know it. So they won't come to you or anything. So force, anything that tends to change or changes the motion of a body. Okay. Weight is a unit that we never represent the heaviness or the mass of an object. Density, of course, is how close things are packed. Mass is, you can read it as good as I can, but pressure measures the intensity of a force exerted on a specific area. We have two standards. We have the U.S. Imperial and the U.S. Customary, which is also called the inch, pound, and gallon. And of course, here we have one unit in the English Customary or U.S. Customary, and that's the pounds per square inch. So that's what we'll be dealing with a lot here, but we will compare them. And what's becoming pretty standard is, and then we have what we call the SI unit, the International Standard Unit, and they deal with newtons. They deal with pascals, which is a representation of a newton. You'll see pascal more than you will newtons. In terms like bars, torrs, and stuff like that, that's used to represent these all these different units. And what we'll have here, and I'll put that, make sure that gets on there, is a just all your cell phones, by the way. You look at the App Store, every one of them's got a conversion calculator on there for you. I know I got one on my phone where you can put units on one side and it converts over for you. Most of your, a lot of your indicators, pressure, especially pressure indicators and flow indicators, is kind of like what they used to do when they tried to convert us over to the kilometers instead of the miles. And we'll look at these. Just about all these indicators now have two units on there. They have an SI unit, and then they have a U.S. Customary unit on there. Thank goodness. Pressure. This is the amount of force extended on an object divided by the area. We have three types of pressures we'll look at. We have atmospheric pressure, we have gauge pressure, and then we have what most people call a vacuum. Okay, and we'll look at the difference between those. Atmospheric pressure, of course, most of y'all already know this, right? 14.7 or 14.69 something. It's a pretty long number, but just about everybody calls it 14.7 psi, and that's the average pressure at sea level. And then, of course, that would be 101.325 kilopascals. So we'll look in a minute at so pascals is something that we use. It's very standard to measure pressure, but that's a metric. It's a metric or international standard. And that's the problem we have, is that probably 95 or even more % of the countries in the world don't use our standard of pressure measurement. So we're so dang stubborn that we still want to use inches and feet and pounds and gallons and pints and all that kind of stuff. And so, you know, you say, well, what's a pint equal to? All right. Well, a milliliter is a thousandth of a meter, right? But we're a foot, 12 inches at a foot, you know. So let's look. By the way, so we'll look at some of the other standards we use to measure pressure. So these are some of our uses: pounds per square inch. 1 pound of force exerted on an area of 1 inch. So we're going to have to learn before we can convert psi over to a force. We're going to have to understand how to convert area, right, or calculate area. Pascal, that's 1 Newton exerted on an area of 1 meter squared. Does it have Newton up there? No. That's probably in your, let's look up a Newton. NW2. The SI unit of force is equal to the force that would give a mass of 1 kilogram of acceleration of 1 meter per second, and is the equivalent of 1,000 dimes, 100,000 dimes. So this is a Newton. So it's a measure of what? Force. Newton's law. That's a law of it. Are we okay? And it's in there. Where's my PowerPoint at? That's not it. Did I exit out of it? I guess I did. So normally what we don't do, but notice the Pascal and the Newtons is the same thing, right? So a Newton is 1 Newton exerted on what? 1 square meter. A bar is equal to what? 100 kilopascals. A torr is equal to 1 millimeter of mercury. Then we have inches of water. We're not going to run into that very often in fluid power, but you will run into inches of mercury. Anybody seen inches of mercury? Where? No. Inches of mercury. You ran into it. Usually barometric pressure, anytime they give you barometric pressure on the news, when they start talking about low pressure and high pressure, that's in what? Inches of mercury or millimeters. And of course your blood pressure is this on this too, by the way. This is a conversion chart. So this will be made available to you. You can print it off if you want to. I'm pretty sure. I don't know about, like I said, I don't have the little book. It's been 5 years since I taught this, and we can't find a copy of it. So anybody got the little tiny reference book? Nobody got that yet. I don't know if it's got a conversion chart in there, but we'll do that. What's that? Don't know. So PSI, then you can say, well, PSI is equal to 6,898 pascals. So we're not going to use pascals a lot. We'll use what we call kilopascals. And y'all, have y'all had the intro to engineering yet? Y'all had the intro to engineering? Have y'all got any metric prefixes? The milli, the micro, the nano, the kilo. So if I've got a big, large number, I can convert it to a kilo by just moving the decimal point to the left 3 times, right? So that's why when we use pressure, we use kilopascals all the time, because what that is, because if I went from 100 psi over to pascals, then I'm going to take 100 and multiply it by 6,895, and that's going to be a lot. It's going to be a real big number. But if we do it in kilopascals or we do it in megapascals, so megapascals, we take the number and split it, move it over 6 times, right? You understand? And then kilopascals, we would take the number and move it over 3 times. So pascals is a very, very often used measurements of pressure. And what we'll look at when we look at some of these pressure gauges, we'll see normally they have 2. Now look at a bar. What's a bar? Now what they did, how they came up with a number for a bar, I don't know. Well, you can see, because a bar is equal to exactly what? Pascals. It's equal to 100,000 pascals. So we use bars a lot. So if I've got 1 bar, that would be equal to 100,000 pascals. What's nice about the bar, too, it's real close to atmospheric pressure. If you look over on the right, notice PSI is 14.5 is the conversion factor for, y'all see where I'm at. So if I was going to go from bars to PSI, I'd multiply it by 14.5. Now atmospheric pressure is what? 14.7. So if we have 2 atmospheres, how would you, what would that mean? Well, I would take 14.7 and I'd multiply it by what? 2. And that would be 2 atmospheres. So that's a very popular way of generating pressure too. The ones we're probably interested in is normally we use millimeters of hydrogen, millimeters of mercury to indicate a vacuum. That's the most popular method of indicating a vacuum. Of course, here our most popular way of indicating pressure is using what? So what do you inflate your tires? PSI. So that's what you will use that exclusively. But you got to understand that when you start getting in a lot of these companies now, like Mercedes is not a U.S. customary company. Just about everything they have down there is using what? International standard of metric system. So they're going to be using bars and newtons and pascals and stuff like that. Fortunately, odds are they'll have 2 meters because over here, and you'll see, I think it's on the next slide. So you can see what most of your meters are doing now, right? You understand? So notice this one. This one right here, what does it have? It has, kilograms per centimeter squared, and it also has what? PSI. This one has kilopascals, and it has bars. This is a vacuum meter, by the way. You notice something different? So on pressure, 0 is on the left. On the vacuum, the 0 is what? On the right. And of course, they're using what? They're using inches of mercury, or they're also using bars, or kilopascals and bars. Y'all seen this guy? Huh? Well, that would be a different situation there, but I'm sure that would be around. I'm not. Yeah, I'm sure they do. I know you're not lying to us. Yeah. So there's all types of gauges out there that represents pressure. Now, what unit is it in? If it's a vacuum or pressure, is it in TSI or is it in? It's your, yeah. So, I know y'all seen these things. These are pressure, and you get this at the doctor. And so they say your blood pressure is 128 over 70. What is that? Not PSI. If you put 128 pounds of pressure in your bloodstream, it's going to bust that thing's out, right? You understand that? So if you look up right on the left-hand side, it says mmHg. So what's it measuring? This measures in millimeters of mercury. So that's what it is. So actually, there's a conversion, by the way. So actually, if, what this would be is 128 millimeters of mercury would actually equal to 2.48 psi. Yeah, and then your bottom one, y'all know what the top one is. What's the top one? Now, what is that though? That's when it's beating. That's when your heart's beating. The bottom of them is the pressure between beats. Yeah. So, so the bottom one would be the pressure between beats. So 1.36 psi. So that's would be if it was converted over to psi. By the way, this conversion is kind of different. So I could take this guy right here, which is millimeters of mercury, and I can multiply it by 0.01934 and come up with those two numbers. Now you notice I'm dividing one of the slides like that, but I've multiplied this so I come up with the same answer. What you got in engineering, we got something called the reciprocal of a number. What's the reciprocal of a number? It is the opposite, but if you divide a number into one, you always come up and get the opposite. So that means if I have a multiplication problem, I could take the reciprocal of what I multiply by, and I could change it into a division problem. So if you took the reciprocal of 0.01934, it would come up and be 51.7. So instead of multiplying by 0.01934, this guy divided by 51.7. But if you took that 0.01, if you got your calculator, yeah, I'd take 128 and multiply it by that 0.01934. It would come up and give you these same answers. So yeah, you run into this all the time you go to the doctor. You run into millimeters of mercury. Everybody okay with work? This becomes very, very important. Work is done when a force moves some distance. Everybody okay? Work is the force times the distance. So guys, we don't change work. Y'all understand? So you notice the guy, when he was doing his hydraulic jack, what was he doing? He was going over a straighter, a longer distance, and he was doing it a lot faster. And over here on the jack side, it was going a real small distance, and it was going real slow. Was we increasing the work? No. Work in equals work out. But what we did is we did what? So if your force goes down, your distance goes up, right? You understand that, which is pretty interesting. So we don't change this, and these are our formulas. So work is equal force times distance. We'll look at this in a minute. This will explain a lot. Power is equal to force times the velocity. We'll use that. It's force divided by time. But time and speed are the reciprocal of each other. So if I took the reciprocal of time, I get speed, right? You understand? So that's where they came up with those two formulas for power. So in electronics, we use the bottom one. In electronics, our force is called voltage, and our speed is called current. So in electricity, if I want to calculate the amount of power I'm producing, then I can take the voltage that's providing the force, and I can multiply that by the amount of current, and that would give me the power that I'm doing. What's that? Well, if they put a clamp on it, then what do you mean put a clamp on the ammeter? Yeah, it's a clamp on the ammeter. All they're doing is measuring. It's really strange. You're not actually measuring current. What you're doing is you're measuring the strength of a magnetic field. And the strength of the magnetic field produced by a change in current is directly proportional to what you, yeah, it's directly proportional to current. And then you have to know the voltage out on the output of your amplifier. Yeah, so you have to know that you have to know the voltage is coming out of your amplifier, and then you can use a clamp on ammeter, and then you could check the power. Are we okay? Yeah. So we're okay on these formulas, very important formulas. And what we can do and what you learn after a while, anytime we got a basic formula, what we can do is we can put it inside a little thing like this, and we'll look at that, and that'll give you 3 equations. So let's go back. So this is the main law of fluid power. This right here. This is what makes fluid power work. This is called Pascal's law. We'll look at several laws. It's like in electricity, we have our main laws. We have Ohm's law, and we have Kirchhoff's law, and then we have Watt's law. Those are our 3 main laws of electricity, physics laws. In fluid power, we have Pascal's law, we have Boyle's law, and we have Charles's law. And we'll look at all those while we go through here. But this guy right here is covered in the first chapter. This is the most important law that's out there. And what does it say? At right angles. So this is why you got your hose pipe out there, right? And you can go out there and you can take your finger and you can press it in. You turn the water on, you can't press it in anymore. As soon as you put pressure, it's not only at the end of the hose, right? You understand? It's also pushing against the side at right angles all over the place. This is a little better. When pressure is applied to a confined fluid, the pressure is transmitted equally throughout the fluid, and it exerts perpendicular at right angles to every surface in the container. And this is one reason when we have this is one reason if they all pushed in the same direction, it would add together, right? You understand? But if we have a pipe, it's perpendicular to the pipe, but what happens is it's pushing at this point, and right next to it, it's not pushing in the same direction, right? You understand that? So this is why all your big compressor tanks and everything, they're not square, they're what? They're round. So this is an example of applying Pascal's law. This is an irregular shape, but it don't make any difference. It's just like when they showed us that person on the video, they stuck that bulb down in there and they sucked that liquid into it. And when they pressed it, they had holes all around it, and it came out equally on all sides. Of course, you couldn't see it coming out the pipe, but if that had holes in the pipe, it would have came out the same way. So they equally in all directions. Now, flat surfaces, the pressure is going to add together, right? That makes sense. In odd-shaped surfaces, the pressures are not going to add together. There'll be some vectored sum of them. Are we okay? So what is a piston? A piston is just a round pulp-shaped device, right? You understand? So all pistons are round. And then, of course, the bar picking out the top, we call that a rod. So what we're doing is we're applying pressure on the rod, and as soon as I try to push that down, I wish I'd have brought my syringe over here. It's the neatest thing. We can fill it up with air, and we can put our finger on it, and we can compress it. But we put a fluid in there, and you put it on there, you can't compress it. Now, fluids are compressible because there's always something in the fluid. There's always some type of air in a fluid. It's almost impossible to get all the air out of a fluid. But it's so minute that we just can't understand it. So as far as we're concerned, liquids are non-compressible. They don't compress. And you saw the person, they stuck it down there. Like I said, I usually put it against my thumb, and you cannot move the plunger or the rod on that syringe to make it move. We put a gas in there, though, so gases are compressible. So that's one of the big difference between fluid power and gas. Gas, we have to compress it before we use it. You understand that? So this is the formula right here. This is Pascal's law. So it says the force we generate is equal to the area and the pressure that's pushing against that area. And this would generate the force. So that means, okay, if I apply the same pressure to a bigger area, we can generate a bigger force. And the smaller the area that we push against, the less force that we generate. Yeah, so look at, all we have to do is so all we have to do on this is called a formula triangle, and this works for any three-term formula. First of all, we figure out which one is the multiplication. So force is equal to area times pressure. And what they tell you to do, if you got this laying on the table, you cover up what you're solving for. So I mean, if I want to solve for area that would generate a certain amount of force, then I cover up area. It's going to be equal to force divided by pressure. And if I wanted to find out what pressure would be required to generate a certain amount of force with this certain amount of area, then I would cover up the P. So pressure would be equal to force over area, or divided by area. That makes sense. And these guys are real neat, because what it does is all you have to do is learn one formula, and if you can put it inside this, you can solve for the other ones without doing what you learn in algebra with multiplying both sides by this and divide. If it's on the bottom on here, you multiply. It's on the top, you divide. All those rules you learn in algebra. If you can get it one of these guys, all you have to do is what? Just look. So I can say, okay, force, and notice area and pressure are side by side. So force would be equal to area times pressure. Area would be equal to force divided by pressure. Pressure would be equal to force divided by area. And luckily, just about all your formulas in electronics is three-term formulas. So we can use these guys a lot. So force. So if I wanted to move a 1,000-pound load, then I've got to generate at least 1,000 pounds of force. Now, we usually have to generate more because we have losses in the system, and we'll talk about that later on. So 1,000 pounds of force. So if I was pushing that against 1,000 square inches, then I could put 1 pound of pressure would move that. You understand that? So we can take this and we can run this into, so here's the thing. Of course, we've already went through that, right? We okay? By the way, these are the units of pressure. We have forces in pounds. Then we have newtons and newtons, and then areas either going to be in square inches or square millimeters or square meters or square millimeters. And PSI is going to be in PSI, pounds per square inch, pascals, megapascals. And when they deal with the chart, we have megapascals, we have kilopascals, and then, of course, we have bars, too, which for some reason got left off this chart. So this is what they're talking about. This is Pascal's law. So that means if I came over here and pushed down on top of that thing, what pressure would be on everything, on all the walls? What would I have to know first? I'd have to know the area. Exactly right. I have to know the area. So I'd have to know the size of this piston right here. Now, unfortunately, pistons are round. Everybody understands that. So when they give the size of the piston, what do they give it in? Well, or over here we give it in inches. All right. Well, no, not the size of the piston. When they talk about the cubic, when they talk about if they say it's a 300 cc engine, or what are they talking about? That, or a cubic inch engine? The displacement, how much air it moves in one revolution. People don't understand that. You know, of course, so what you're doing is you're defining not the physical size of the engine, you're defining the size of the piston and the stroke. Yeah, the stroke, you're right, because that would be the amount, yeah. So a lot of people don't understand that. So they think it's the physical size of the engine, but when we give out those displacements, we're giving it the amount of air it can move, or the amount of fluid it can move in what? One revolution. Or one stroke. If it was a reciprocating engine, it would be how much it could move in one stroke. If it was one cylinder, if it's multiple cylinders, is how many you can move in one revolution. So what I first have to know before I can figure out the pressure is I would have to know what that was. But it would turn out to be if I put 50 psi on the top, right? You understand? Then it's going to be 50 pounds per square inch on the bottom, right? Y'all understand that? Yes or no? So let's look at this. So force permits the use of power developed in one place to be used in a what? Somewhere else, and allows the force to be multiplied through various piston areas. And that's what we're going to look at. So here we go. So they haven't solved for this, by the way. So what that means is, so notice our piston on the left has an area of what? We call that square inch. So we say 1 square inch. That's why and the piston on the right gives what? It's 5 square inches. Okay. So what that means, if I put a 100-pound weight on the top, then on the bottom, that's going to be 100 times 1, right? Which would be what? 100 psi per square inch. Now this pressure is applied throughout the system. So everything in there gets that. But what we're looking at is the one on the right. It has the ability to move. So that means if I'm doing 100 pounds over here, then that got an area of what? 5. So it's going to take that, and that's per square inch. So I'm getting 100 psi on this side, right? Over there, I'm generating what? 100 psi. It's still 100 psi, but now that's pounds per square inch, right? You understand? So what would we do on the other side? Well, I would multiply that by what? 5. So that means over here, I'm applying 100 pounds and getting 500 pounds. Right? That makes sense. And that's the way we multiply. Of course, what's going to happen, what would happen to the speed of the distance on the one on the side? Right. It's going to be slower and don't move as far. Because we're not changing the amount of work. We're getting the same amount of work. Right? You understand that? We're not changing the amount of power. Power in equals power out. The only thing, and that's a rule of thumb. Actually, power out can never equal power in because that means my system has no loss. But for practical purpose, we'll say power out equals power in. A lot of people don't understand that, you know. And what I say, if I turn on a 100-watt light bulb at my house, Alabama Power has to provide me with 100 watts. Of course, they have to provide me with, that would be if the system was 100% efficient. So it depends on the efficiency of the system. So observations, work out equals what? Work in, power out equals power out, power in. The force is what changes. So here the output force is what? Greater than the input force. If force goes up, distance has to do what? So if work is equal to force times distance, if I come over here and I say, okay, if force equals work, and my work does not change. So if I come over here and did this, guys, if I come over and says, okay, my force is going up on my output, then what's going to happen to the distance on my output? It's not going to travel as far, right? You understand? And also over here on power, if force goes up on my output, what's got to happen to my speed? It's got to go down. So what you'll see is you're over here like the guy on the jack doing what? He's going this far, right? You understand? Over here it's moving what? That far. Over here, they working like crazy, and over here it's moving what? Real slow. But now you're taking this force, you know, over here, and you're multiplying it because if you looked in there, the little cylinder that they're pushing again is a little old tiny thing, and over here on the other side, the one that's actually expanding is what? Is a lot bigger. So we get force multiplication. but we lose speed and we lose distance, right? So anybody got a hydraulic jacket? Well, those are nice. I got two of them. So this is the one we've already worked out. So here we got 10 inches. Over there, square inches. Over here, we got 50 square inches. They're putting 100 pounds of pressure on this side, 100 pounds of force on this side, right? Okay, so what would be my PSI on the bottom? Well, what we're going to take is we're going to take that 100. You're right, but what would be my PSI on the bottom of this, the cylinder on the left? But we'll say, okay, you're on the other side, I'm on the left. Okay. So what would it be? I've got 100 PSI, I'm putting 100 pounds of force on the top. Then that's spread out over 10 square inches. Right? You understand? So that means I would be putting 10 PSI, right, or pounds per square on force on this one, right? You understand that? Yes or no? So what's happening is I'm taking that 100 one over this side and I'm dividing that over what? 10 inches. So if I want to calculate my pressure, my PSI that I'm generating is going to be what? It's going to be 100 divided by what? 10. So that means I'm going to generate 10 PSI. Then this 10 PSI is all over the place, right? You understand? In our piping, all our everything, it's everywhere. But this over here has the ability to do what? Move. Okay, so I'm taking that 10 PSI and I'm applying that to 50 square inches. So my force over here is going to be equal to what? 50 times 10, which is going to give me what? 500 pounds force. So what we're doing is we're putting 100 over here and we're getting 50 over there. I'm sorry, 500 over there, right? You understand? Are we okay? So what's the first thing we have to do? First, we take how much force we're applying to our driver, and then we come up and we divide that by how much surface we're pushing with, right? You understand? The area of the surface. And then we go over to the other side, and then we use that. All we have to do is understand that ratio. Yes, it is. Yeah, it's still 10 psi. We're not, and that's what it says. Pascal law. It says it's applied. It's applied. The same psi is on all surface. So what we do on our output side is we just use a bigger surface. So if we use a bigger surface and we're putting so many pounds per square inch, so if I'm putting 10 pounds per square inch, and over here I've got 5 square inches, then I'm developing 500 pounds of force. So I could literally, if this system was 100% efficient, which means there's no loss. Of course, you can see there's going to be loss because some of that PSI, some of that 100 pounds is going to be lost on the contact between my piston and what? And the sides of the cylinder. So anytime you have friction, you're going to have to overcome friction. And also I've got to overcome my friction on my other side. But just for demonstration principles right now, so I would have to know the efficiency of the system. So all they say is you just have to make sure you have more than what you need. So if I needed to move a 5,000 pound weight, I would just make sure I had more pressure or force available on my output than there. And this is the math. So the output speed and the output distance. So here we're using, okay, so I could have skipped a bunch of math, right? You understand? So what could I have done? I could have took my output area, divided it by my input area, and I got what? 5. And that's my multiplier. Then I could have just took my force on my input, multiplied it by that 5, and then I would have did what? I would have came up with my output. And then my speed, I would just divide it by the ratio of the two pistons. So I have a ratio of 5, so that my output speed would be at 1/5, right? Understand? And my output distance would be what? 1/5. You understand that? So the ratio between those pistons tells us a lot about what we can do with this thing. The higher the ratio, the more force we can generate. But we're not changing the amount of input work. So my input work and my output work are equal to each other. Right? You understand? So it's just like people that walk. If you can burn so many calories, if you can do 1 mile in 10 minutes, then you can go 10 miles in 1 minute, and 1 mile in 10 minutes. Then you go 10 miles in what? I got that backwards. Yeah, 1 hour to do what? The same work. You burn the same number of calories. Because work in and work out is going to be equal to each other. We don't have a work multiplier. We do have a force multiplier, but we don't have a power multiplier, and and people think we have these things called power amps, but you got to understand, we got this other thing called a power supply. So power amps don't create power. You don't understand that? If you got a power amp in your car, they don't create power. They manage power. The power's already there. So you go out there and disconnect your battery and turn your radio on, right? So we're not creating power. We're just taking the power that's available, and with these electronics, it controls that power. So and we have people do that. They exceed the power rating of their system, and they end up with a stereo that sounds awful. So guys, what we got here? So another term that we use a term called the bore. Anybody know what the bore of a cylinder is? It's the inside diameter. It's the inside diameter of the cylinder. So that's why they specify cylinders. They say, and of course, a cylinder is a what? It's a round hollow tube. That's what it is. So one of our main things that we use in fluid power to generate a linear or straight line motion is we use the cylinder. Okay. And so they say this guy over here is a 3-inch bore. But the problem is, so they give cylinder sizes as the diameter. So that means it's got a 3-inch diameter on the inside. We're not concerned with the outside. We're talking about the size of the inside, right? And we're pushing against a 3-inch bore. Over the other side, we got a 5-inch bore. So first thing we got to do is what? Got to find the area. So how do we find the area of a circle? No, what we got to do, not the area. But we don't know the pressure. We're trying to figure out the pressure. You're right. If I was given the pressure, I could solve for the area. But here we don't know the pressure. We have to know the area to solve for the pressure. Now, once I solve for the pressure, I could say, well, what area caused that? Then I could go backwards, right? So we can't have two unknowns in an equation. Okay, we can have one, right? You understand, but we can't have two. So area is equal to pi r squared, and what is r? The radius. So I could take 3, and I could divide it by 2, but it'd be nice if I could go directly from what? From the diameter to the area. You're looking at a circle from the side, and we don't have the. So if I drew a circle like this, so if I drew a circle like that, you see it as a circle. If I look at a circle like this, what does it look like? Straight line. That's a good point. It would be very inefficient. It would be, first thing, it'd be hard. It's hard to seal around a corner. So it's real easy to seal around a circle. But when you come to that corner, it would be hard to make a seal that made a 90-degree. So you always have leaks at the corner. So that would be, I could use area is equal to, well, we're not, that would be the volume. An area is a flat surface. So a rectangle would be length times width. And a square is the same thing, but we learned any side squared because the sides are all. So that's a flat surface. So we're not concerned with how thick the thing is, right? You understand? Of course, that would come into play if I design cylinders, because I can't push 2,000 pounds with a little thin piece of plastic. So the thickness of the piston would determine how much force it can handle, right? You understand? But yeah, I know they do, but especially in pneumatic systems, low pressure, you're not. Yeah. So a good example of a plastic piston is a syringe, and so your doctors use that. So how do we get off on this? Yeah. Let's go ahead and take a 10-minute break, guys. So I could say pi, and this is what would be the diameter. So if I took the diameter and divided it by 2, that would give me the radius. And then if I squared that, that would be the same formula, right? You understand that? Yeah, but let's go a little further. What I'm trying to explain to you is where this number came from. So the number is 0.785. So I can take the diameter and multiply it by 0.785, and that gives you the area. And that's one of those numbers that just floats in your head once you learn them. You know, right now you probably have to look it up, but if you dealt with these all the time, you'd know that number. So what I can do is I can come up here and I can say both the area would be equal to the pi, and then I can say would be equal to the diameter squared divided by 4. That's the same thing, right? You understand that? So what I did is I got rid of the square and I squared both of them. Then I can kind of split this out, and I can say, okay, I can split this out, and I can go over here and, I can say, okay, pi divided by 4 times the diameter squared. That would be the same thing. Well, I can take pi divided by 4, and I come up with 0.785. So what you can do right off the bat, and most of these things you can square in your head. So 3, what's 3 squared? 9. Okay. So what I can do, and I can say my area would be equal to the diameter squared times 0.785. And but I can't tell you, I can't tell you when I learned that last time I taught fluid power. And of course I've used it, and now I don't. Now I got 0.785 where in my head, yeah. So the diameter squared by 0.785. So you probably have to have a calculator, but you could do this longhand. Most of the time, you could 3-inch board. That'd be 9 times 0.785. You know, you could take a piece of paper and do that. So what do we come up with the diameter? So what would be the 3-inch? What would be the area here? Y'all got your calculator? You ever have to have a calculator in this class? Was that was on the yeah? And if you're taking electronics, you got a calculator by now. We're gonna you use that calculator. So what y'all got? No, it's 7.065 square inches, right? And what's our diameter on the other? What would be our area on the other side? So this would be 25 times 0.785. Calculators. Don't you have calculators? By the way, you don't eat in my classrooms for obvious reasons. What's that? 9.26? Okay, 19.6. Okay. So what would be my ratio between the two? Yeah, 19.6 to 7 point. Y'all got calculators? Somebody's got a calculator. What is it?
So we're supposed to take the 19.6 and divide it by 7.06. 7.6, huh? See, a lot of these you can get, I mean, it might not be perfectly accurate, but a lot of these you can get close to in your head. What's that, 2.8? So first thing I would do is I'd say, okay, what's my pressure over here? I'd say 200, right, divided by 7.065. And this would be my pressure. So what would be our pressure over here? What's that? Okay, so 28.3 PSI. Then what I'm going to do is I'm going to take that 28. So my force over here is going to be equal to 28.3 PSI times 19.6. So how much force could we generate over on the right-hand side with 200 pounds of force on the left-hand side? By the way, most of y'all, it's one of the standard apps that come on what? So if you got a cell phone, guys, you probably got a what on there? Calculator. So what did we come up with? 537.7. 19.6 if that's the area. Of course, I'm complaining about y'all not having a calculator, and I don't have. Of course, I got my cell phone. So everybody's got a cell phone, right? 555. Yeah, that's what it is. 555.6. Yeah. Now I didn't do that in my head. I've seen the slide. I don't think I'm smarter than I am. Oh yeah, that's what I do. I go to sleep doing formulas in my head. So 555.5, and here's the math. 555.6. Now this is considering the system is 100% efficient, right? You understand that? Actually, it would be less than 555. So 536 would probably be more correct, taking away the inefficiency of the system. And no matter what people tell you, you always consume more power than you produce. I'm sorry. You always use more power than you produce. So power in will always be more than power out. So if you're running a 400 watt amplifier, you got to give that amplifier more than 400 watts off your power system, right? You understand that? That's when you get these people that run 2 alternators out there, and they have 2 batteries in their car. They have one alternator to run their stereo, and one battery and alternator to run their stereo, and one to run their car. So people don't think that. They think a power amplifier, these power amplifiers actually increase power. No, they just use power. Yeah. What's the size of the cables running from your battery? And what's the size of the one running from to your speakers? They're a lot smaller, but what you got to understand, they're delivering that power at a lot higher voltage. And of course, amps is equal to P over V, so that means the higher you can make your output voltage, the less current is going to be required to produce that power. Yeah. Pressure on a 1 inch squared area is transferred equally throughout the system. Pressure on a 5 inch is 5 times greater. So the speed and distance is going to be 1/5. So your force multiplier is going to be your speed and distance divider, right? Because we're not creating work. We're just taking work and just changing the form of it, right? You understand? And like we was talking about, doing the walking. A lot of people walk, but they have to walk a lot further to create the same calories. We have 2 types of flow, and this is one of our main losses in our system, is trying to get the dang flow to from the pipe. We call it piping or tubing. So normally we don't have our source of our pressure beside our actuators. So your pumps or your compressors are going to be way over here, right? And then your actuators got to be over there. So how do we get the pressure or the flow from my power source through lines, right? To these lines. Unfortunately, when you send stuff through the lines, you have two types of flow in the line. Out on the edge, you have turbulent flow because it's running against the sides of the pipe. On the inside, you usually have laminar flow or parallel flow because it's in the center, and it's being lubricated by what? On the outside. So we have two types of flow when we move it through control valves. So we know in an electrical system, the basic makeup of a circuit in electricity is we have to have a source of our power, right? We have to have a pressure source. We call it voltage. So we have to have a source of voltage, and then we got to have a load. So the lights would be a what? A load, right? But I've got to be able to get that from my voltage source up to that. So we have these things we call electrical conductors. Now, normally we have some way to control the flow of what we call current. So what do we have on that wall over there? We have a light switch. So in fluid power, we use valves, just like your faucet. Your faucet is a valve. And what can you do with that? You can turn it on or turn it off, and we have what we call proportional control valves, which unfortunately we don't have any of those here, which you could actually control the flow, right? How fast things move. All ours are going to be what we call digital. They're either going to be on or off or left or right, and we'll talk about that. So what we do with these flow control, with these valves, is we can either cut it on or cut it off, right? You understand? Or we can control the direction, which means if I'm going to move something left and right, then I got to put pressure. I got to have some way of swapping which way the pressure's on. So your control valves, they're going to create turbulent flow. So anytime we have turbulent flow, we're going to have loss in the system, right? You understand that? So occurs whenever there's resistance to the flow, actuator, orifices in the pipe, just fluid moving through the pipes. Right? Are you okay? So this is why your pressure, you got to have a higher force. You got to generate a higher pressure than what you calculate to move that load, because you got to do what? You got to compensate for the what? Loss in the system. You guys, you might need 50 p over here. Instead of what we had a while ago, we had what was our PSI a while ago? Did I leave it up there? Did we calculate our PSI? So 28. So over there, instead of having 28, I might have to have 30 or 32 to move that 537 pound load. I might have. I got my glasses up so I can see my computer. That 537 pound load over here. We said, okay, we're going to get 28 point something PSI. Well, actually, in true life, we would need a little more, right? You understand? To compensate for what? The losses in the system. Good, guys. Same thing with horsepower. Yeah, and what they do when they usually measure horsepower, it's best to measure it at the rear wheels, on the tire, because you're actually putting more. Your engine is putting more horsepower, and you're using more horsepower in than you're getting even through your engine. So we have losses in our engine, and we have losses from just getting it from the drivetrain and the gearbox and the transmission, everything you got to go through to get to the end. I like those tractor pulls where they have them engines running into engines, and ain't no telling how many horsepower. I don't know. No, I haven't. So here's the math on the one that we just did, guys. So y'all okay? If that's okay. We talked about that. How did I get backwards? Okay. So this is speed. So there's two things we need to understand. We need to understand how fast the piston or how fast the actuator is going to move, right? You understand, and also how much force is it going to be generated. So what determines how fast a actuator moves? Has nothing to do with it. Not pressure. Pressure don't determine that either. Even though we got to have this, right? You understand? That sucker on the top, that flow. Well, the flow, how fast things move. So when you start looking at pumps, they're rated at pressure, but they're also rated at flow. If you ever bought a compressor, cubic feet per minute. Cubic feet per minute. Well, that determines how fast things move. It don't determine how much force you can generate. It determines how fast things move, right? So flow is the main determining factor of how fast things move. But we can't have it, so where's force in there? Force is not even in there. So what three things determine the speed? The flow rate, right? You understand that. The area, right? And that's going to give you the velocity. Well, actually, two things control the speed. So V is velocity. No, it would be gallon. And over here on the USA customary, we'd use gallons per minute. That would determine the flow rate. Okay. Yes, you do. Every compressor that I've ever seen gives you two things. One thing they give you is what they call standard gallons per second, or per minute, I'm sorry. And that would determine how fast your things move. What's really neat, so we can control the speed without changing the force. So we have these valves we'll look at called flow control valves. What does flow control valves do? They don't change the force. I can still generate, they change how fast it moves. If I can change how fast it moves, then not only can I get the same force, but I can also now set the speed. So that's one of the valves we have available called a flow control valve. And we'll see those over there. Are we okay? Huh? That's the formula for speed. Force. Or what pressure is required. So it's what we would use to figure out, okay, I've got this compressor or I've got this pump that can put out 3,000 PSI. And I need to generate 5,000 pounds of force. What size cylinder do I need? Then you could use that, right? You understand? So you can transpose that. So if you know what force you got to need and you know the area of your cylinders, then you could calculate how much pressure do I need, or vice versa. If you know your pressure and you know how much you're going to need, how much you're trying to move, then you could calculate the cylinder you need, right? You understand? This is the formula not for force. This is the formula for what? Speed. How fast it moves. So what two things determine the speed? The flow rate and the area it's pushing against. So the bigger the area, we would get more speed for the same flow. Right? Everybody understand that? I'm sorry. The bigger the area, the less speed. Yeah. So if I solve for speed, what is speed going to be equal to? Velocity is going to be equal to the flow rate divided by the area. Now that's torque. Now torque is another method of measuring horsepower, or how much force you generate. So torque is a twisting motion. Okay, y'all understand that? So torque is a way we measure force that's in a circle. So it has nothing to do. How fast it moves is one thing. So if I'm out there using my impact wrench, right? If I adjust the flow, it's going to move slower, but it's going to generate the same force, right? You understand? So the speed doesn't have anything to do with, well, the force. What determines the force? No, what determines the force? Flow has nothing to do with the force. The pressure in the area. Okay, how much pressure? I didn't hear you. Yeah, so speed is not in that formula. Velocity is not in the force formula, right? You understand that? Okay, so force does not determine the speed. What determines the speed? Huh? How much gallons per minute you move, and then what area you're moving that against. So the bigger the area, the slower it's going to go. Yeah, you got to size the piping for the flow rate you need. Because if you use a size that's too small, then you get a lot of turbulent flow and you get a lot of resistance in your tubing, right? You understand? So this is why if I'm going to control a lot of flow, I use a watt. Bigger. It's just like wires. Our flow is current. So the more current I'm trying to control, the bigger the wire. The more current I'm trying to control, the bigger my power amp has to be, right? The bigger the transistors have to be that's controlling that power because they're controlling more current. The bigger the flow I have, the bigger the orifices inside your valves and everything has to be. So the size of your pipe does not determine the pressure. The size of your pipe determines how good you can do what you can maintain or get that flow. Yeah, but it's got the sides have got to handle the pressure. The size of the pipe, the inside diameter of the pipe has nothing to do with the pressure. It determines how fast you can flow. What determines the pressure is the thickness of the walls. yeah, y'all understand that, because that's trying to keep that pressure in. So, and in electronics we have insulators, and what determines how much push it can push in, of course, is what the insulator is made out of. You know, so if I have a steel pipe, it's going to have a thinner wall than a concrete pipe because of the stiffness of the metal. So we have different insulators. We have different materials it's made out of. Depends on what material it's made out of, how thick it has to be to keep that flow in. So yeah, the size of the piping would don't come into play for pressure. The size of the piping comes in. The inside diameter would determine the flow, right? And these are flow rates. Cubic. So when we start talking about flow rates, we're talking about cubic feet, because you're talking about a volume, right? You understand? So this is where the length times the width plus the height would come into play. Are we okay? So we got inches, we got gallons per minute. Is that over there? That's used a lot. I don't see gallons per minute in there. Do y'all see that? Most compressors are labeled in gallons per minute. Most of your ISO, the SI units are going to be liters per minute. Are we okay? So they've left out whoever did this. I didn't do this. Everybody okay on force? Trying to get through with chapter 1 today, guys. So what we got? Everybody okay on force? Okay, this is about the third time it's been in the PowerPoint. So everybody okay on area? So this is how we came up with that 0.785 by going from the diameter, right? So the diameter square by 0.7. You can use pi r squared. Now what's pi? Yes. What is pi? Pi is an infinite number. So we don't know what pi is. So anybody tell you they know what pi is, they don't. Yeah, it's still going on. Yeah, so pi is an infinite number, and it's a non-repeating number. It's an unreal, it never repeats. Well, they hadn't yet. What is pi? But how did they come up with pi? Pi is if you take the circumference of any circle and you divide it by the diameter, it always comes up to give you that number. You know, they had a guy on one of those Steve Harvey shows, a little tiny. I think he had memorized pi to 100 digits. Now, I didn't check him on it, but there's a website that's got it out to 1,000,000 digits. because it's non-repeating. It don't fall into a repeating pattern. Yeah, it never falls into a repeating pattern. And on the person of interest, that was one of my shows. I used to like that. Harold came up with something. Some of y'all probably heard me. They said every number that's ever been written is in pi somewhere. Somewhere your Social Security number is in consecutive digits in pi. Your phone number's in there. Every number that's ever been written is in pi. Ain't that neat? I don't know. It's one of those numbers. We do have. So what's pressure? Being pushed, right? Yeah. Of course, we have to have pressure before we have force. We have to have two things, and we have to have force before we have motion. Okay. So we can't have one without the other. Work together. You can't have one without the other. You cannot have a force without a pressure. You can't have a pressure without creating a force, which is pretty neat. There's only one thing that I know of that changes its pressure with speed, and that's wind. So, so that's why when we get a hurricane coming through and it starts pushing against your house, it generates a pound per square inch, right? Don't know. That's a good question. We have different types of pumps that use. We have inertial pumps that use the slinging out section to generate those. In fact, a lot of your pool pumps are that way. So if you ever looked at a pool pump, it's just a spinning blade, and the water comes in the center, and then the blades go out, and it just spins. And what happens is when it spins, it generates inertia. Turbine pushes back where an inertial pump pushes out. So one of them creates what we call radial pressure. One of them would be actual pressure. Yeah. So radial pressure is at 90 degrees, and then actual pressure is in parallel. In parallel. So gauge pressure, this is what most gauges do, so they're actually giving you something wrong. So what gauge pressure just basically ignores is atmospheric pressure. And unfortunately, we gotta overcome atmospheric pressure before we can really do anything, right? So when a gauge pressure, if we got gauge pressure, when it's showing 0, there's actually 14.7 psi available. So if you wanted to find your true pressure, which they call absolute pressure, you would add 47. So if you had an absolute pressure gauge, while it's sitting there, nothing's happened, it would show 14.7 psi. Gauges show what? 0. Sometimes it's very important, but to us it's not, because there's so little difference between what's going on that most of your gauges just use regular gauge pressure. Mm-hmm. The sensor. Odds are it'd probably be your sensor that's giving you the problem. Yeah. Are we okay? So we already talked about this. Everybody okay? By the way, what's strange about a cylinder is, and later on we'll look at what we call rodlet cylinders. And what we're going to do, guys, is we're here before long we're going to go over to the robotics lab. Well, actually the mechatronics lab, and let y'all see a fluid power system in play over there, and let y'all watch the manufacturing lines. And we're also going to come over here and look at our lab next door. But anytime we have a cylinder, a rodded cylinder, and we'll let y'all look at what we call a rodded cylinder. So the cylinders that we have over here have a rod on them. And what's the purpose of the rod? Well, it's to transfer the power from the piston to the outside world, right? You understand? So the rod comes out the side of the cylinder. Now, what do you notice about the area? Well, the area that extends the rod is going to be greater than the area that retracts the rod, because that rod's in the center, and what we've lost that area of the rod when we retract it, because it's pushing there, the rod's here, so that area that's occupied by the rod is lost. So what does that mean? No, it's not a vacuum. What does it mean? Well, it means my extend force is going to be greater than my retract force. Y'all understand that? My extend speed is going to be slower than my retract speed. Your retract speed will be faster, because it's what? Flow divided by area. So my retract area is going to be less than my extend area. So that means the thing's going to run at two different speeds. Now, we do have ability to compensate for that by using what we call flow control valves. So what we can do is we can put a flow control valve on each side, and we can run the flow differently, right? We can't do much about the pressure. We can't do anything about the force. So on these guys, the retract force will always be what? Smaller than the what? Extend force. So this has a little more mass. So what would I need to know? Two things. I would need to know the bore. The bore would give me my extend force, and then when I calculate my retract force, I'm going to have to subtract the area of the rod. So what would be my ratio for extend, and what would be my ratio for retract? So what would be my area, what would be my area for extend, and what would be my area for subtract? Got to have them calculators, guys. Pull out your cell phone. Pull up your calculator out. Come on. Yeah, so we would do what? So my area extend would be 2.5 squared times 0.785. That would be my area to extend. Anybody got a calculator to do that? By the way, I looked at the first test, and guess what? There's a lot of these questions on there. And I think there's a worksheet too, guys. I need to talk to Miss Wilson. Huh? This before Miss Wilson got promoted. This was her class. She's the assistant dean of career tech. So she don't take classes. She's my boss. Yeah. She's my boss. So what do we come up with? So there's a lot of worksheets on there. There's a worksheet for every chapter, and I need to find out how she works those and how that comes back to be grading. Unfortunately, the guy that took her place to teach the class passed away last term, and that was a shock. So what we got? Anybody have any Mr. Perry's classes? Huh? What we got? 4.9 square inches, right? Now what we're going to have to do to calculate our retract, so my area retract is going to be equal to the same thing, 5.9 square inches, right? Minus, and then I'm going to have to calculate the area of the rod. So this is going to be 1 squared, which is 1, times 0.785, which is 0.785. So minus 0.785. Y'all understand how I did that? Because 1 squared is what? 1. 1 times 0.785 is 0.785, so this is a real good example here. And then this would be my retract area. So my retract area is going to go down, which means my retract force is going to be, and we can go watch this, by the way. If we take the flow control out, we can watch we can watch it retract faster than it extends. I don't think we got any flow control on the one we'll look at next door. I mean across the road. So what's our retract area? Anybody got it? Four point 4.15. Okay. 4.1. Yeah. And then this would be square inches. So then when we use this to calculate speed, you'll notice it's going to retract since velocity is equal to flow over area. That means it's going to retract faster than it's going to extend. It'll extend slower, and then we'll generate more force. Of course, we can't calculate force unless we know what. What do we need to know to calculate force? Force is equal to pressure. Yeah, pressure. So this is it. Here they gave a pressure of 750 psi, which is a lot. Well, hydraulics, that would be low. Probably the smallest pressure on a hydraulic system I've worked with was 1,000 psi. And the highest I worked with was 3,000 psi. But it could be more. What's nice about fluids is they don't care how much you compress them. Gases, we have problems because if you compress them too much, what will they turn into? Liquids, yeah. So that's why liquid helium, liquid hydrogen, if you do welding, you deal with a lot of liquid gases. And we have a problem with air too. What's the problem with air? Well, all air has moisture in it. And of course, the amount of water an air can handle depends on the volume of the air. Right? You understand that? So when we start compressing the air, we decrease the volume. What's it going to do with the water? It can't hold the water anymore. So what's it going to do? Don't throw it out. And it gets in everything. So that's a big problem we have. Condensation. Also, we get condensation because anytime you compress something, it heats up, right? You understand that? And then when it cools down, it's going to do what? It's going to condense too. But then we have the problem with when you compress it, it can't hold the water anymore anyway. So normally we use different types of fluids. We use different types of fluids. For one thing, we use oil most of the time, right? And oils have a lot lower freezing temperature. And then, of course, they have special mixes of oil that you run. It's just like when you buy oils, you buy it for where you run at. So if I lived in Denver, then I would run a different viscosity of my oil than I would do down here. Weather temp or something like that. If I lived in Alaska, I would run a different viscosity oil than I would do down here. So that's the same thing. It depends on your top number and your bottom number. So your top number is basically for heat, and your bottom number is for cold. So that means you have a lighter oil that don't freeze, and then you got a heavier oil that gets real thick, and then of course it separates in your. So when it gets real cold, your heavy oil moves up, and your light oil's on the bottom. So your oil pump pumps out the light, and then when it gets hot, everything comes up. So it's really neat. when they came out. Used to, you know, you had one oil, but now you got the dual viscosity oil that we. And they, so Elko here. So what they did here, what did they do? So here, when they calculated the pressure using 750 psi, they came with 3,682 pounds of extend and 3,094 pounds of retract. So you got to size both one. If you're going to move a weight if you got to move the weight in direction, if you're going to move a weight in something in two directions, then you have to do your calculations for your rod side, right? You understand, and not your unrodded side. So this is one advantage of a rodless cylinder. A rodless cylinder would generate the same force in both directions. So we've already did this. This is Pascal laws for cylinders. Are y'all okay? So y'all gonna have to work some of these guys. I'm sorry about that. On the first test. This is the math, by the way. We already talked about this, right? Smooth flow, laminar flow is smooth flow. Usually in the pipes, laminar flow or parallel flow is in the center of the pipe, and then you have your turbulent flow on the outside of the pipe. And this is the twice that's been in here, isn't it? Everybody on power. This is no. Oh yeah, no. One of them's just it's a 3D printer. Huh? No, they clean off 3D parts. We have a 3D printer over there. It's a silicone printer. Not that I know of. There might be one downstairs. I don't know. They do welding downstairs. This building this is the one-stop center. This is used for industrial training. So just about everything in here is used for industrial training. So when an industry comes, oh no, you have to take an industrial training class. Why, they new or something? Yeah, they are. Yeah. All right, guys, let's talk about fluid power. So horsepower. How did horsepower come into being? Anybody know? You're right, but why did they ever have to come up with that? Well, the problem is that when they invented the steam engine, people didn't understand steam engine. So what they wanted to do is they wanted to come up with a method where they could compare a steam engine over to what was the primary mover at the time, horses. So they hooked up a bunch of horses, put a big weight down in a whale, and they started having those guys pull that weight up out of the whale, and they timed how long it took them, force times distance, right? You understand that? And it came up, the average horse could move 500 feet per foot-pounds per second. That's what the average horse could use. So that became what we know now as a horsepower. The horses are strong. Yeah, they were. Sometimes it amazes me. I've seen some of these people that climb on the back of these horses. I say, how in the world can that horse carry them people? But this was a standard farm horse, so this wasn't one of those little Palomino ponies or stuff like that. So these are pretty good sized horses. These wasn't what they call them, quarter horses that you see a lot. Those are bred, you know, quarter horses are bred. Just a big full-sized cowboy horse. In power, in power, in electrical power, 1 horsepower is equal to 746 watts. So I take the electrical power and I divide that by 746, and that would give me the number of horsepower. If I was dealing with electrical power, so what we're doing is we're taking, so horsepower is a physical power, right? Well, when electrical, we calculate electrical power, we say that's equal to force, which is our voltage, times our current, which is our speed, which has nothing to do with how much horsepower a motor can generate. So if I knew my currents that was required by my motor, and I know what voltage that runs over, I could multiply them the two together. And then I could take that and I could divide that by 746, and that would give me the equivalent horsepower that motor would generate. Okay. So normally when we buy a motor, we buy it according to a horsepower, right? You understand that? But when we look at the nameplate, you'll see it gives you not only a horsepower, but it'll give you what we call the full load current, which means if it's a 5 horsepower motor, that's how much current it'll pull if it was developing 5 horsepower. And then it'll give you the voltage that the motor is designed to run on. And they should come up to be fairly the same, but they're not, because what's going to happen is that we're going to compensate for the efficiency of the motor. So usually when you take the current and the voltage, you multiply it, you're going to come up with more over here than you actually get. So you might calculate, 5.3 horsepower, and it's a 5 horsepower motor. Okay. In fluid power, what we do is we take the PSI, so pressure times speed, right? You understand? And that would give us power, and then we convert that into horsepower. Okay, so what would that be, guys? So it would be horsepower would be equal to PSI times the gallon per minute. So that's the same as in electricity. We use force, which is voltage, right, times our current. Okay, here they're using pressure, which generates force, times the speed. Same thing, right? And then we do what? Then we divide that by 1714. And then if we know the efficiency of the system, we can multiply that by times the efficiency, which would be a fraction. And this is the formula we use to calculate fluid horsepower. Now, do you have to memorize these formulas? Well, if you were in the field, yes. But if you're taking this, if you deal with it a long time, you're gonna memorize them, right? So what we do is you're gonna buy this little old book. You need to buy the book, right? Because what's in that little old reference book you're gonna buy? Not that one, the little thin one. Nobody's got it yet. It's supposed to be. It's on your brief. It's a little pan. That's what it is. It's a reference guide. And what's it going to have in there? It's going to have all these formulas in there. In this class, you're welcome to. If you don't have it, if you don't have the little book, what are you going to have to do? You got to learn all the formulas. If you have the little book, you're going to have to do what? Yeah, but you can't write them. You can't write them down. You can't. When you come and take a test, you can't bring any written material in. You can't. You're not going to take tests from notes, right? You understand that? So you'll have to memorize the formula. So I highly recommend that you. Well, no, you buy the book. Yeah, not the textbook. Got to be real careful. Normally, we don't allow y'all to use memory calculators because one thing, you can put a lot more stuff on there than you can put. So we don't allow y'all to use cell phones and stuff like that while you take a test, because anytime you got something called memory on there, what can you do? You can put a lot of answers on there. So, oh yeah, it was. So guys, y'all go ahead and we're going to stop the lecture right now. We'll finish this up. I was hoping we can get through with this, but y'all answer a lot of good questions. So y'all stop asking questions now. We could get through the lectures. No, y'all answer all the questions y'all need. But what we're going to do is we're going to let y'all take a break, and then we're going to go over into our lab over here and let y'all see our trainers that we'll be using. And then what we're going to do is everybody's going to get in their car, your vehicle, and we're going to go over to the hall building. Y'all know where the hall building is at? Where the robotics is at? Yeah, and that will let y'all, we'll go into the mechatronics lab and let y'all look at our 2 manufacturing line and look at the fluid that uses is pneumatics. And by the way, pneumatics and hydraulics are so similar. They're not the same, but they're similar enough that once you learn one, you would have absolutely no problem picking up on the other. It's just that hydraulics is a lot more dangerous than pneumatics. Okay, guys, y'all go ahead and take a break, and then we'll go. I don't know. It's in the syllabus. It's in the brief. It's on Blackboard. But everybody's got a brief, right? The name of the book is Fluid Power Data Book. You hear that, Justin? Fluid Power Data Book.